dynamic equations, dynamic motion primitives, that allow kick trajectories to change shapes depending on the goal state. Sung and All designed biopoint trajectories with different states that allow them to generate different kick trajectories. Q-learning from Wang and All was also used in simulations to design kicks. Xu and Melman used the configuration space of the robot to discover the reachability the robot had to kick a ball in a certain direction and design a state machine to plan the kick motion generation. I also want to add that static kicks have also been an important milestone reached to generate motions during soccer games, but it's not easily generalized to different kicks because of stability concerns. These different research ideas have dealt with kick motion generation and stability, but it does not deal with integration of motions such as walking to minimize the amount of time it takes to generate these motions and utilize the momentum of walk gates to generate stronger kicks. So, although a variety of kick engines have been implemented over the years, there are none that demonstrate omnidirectional kick and kick motion while walking. We therefore, in this research paper, propose multiple ideas that fill in the gaps of kick motion research. First, we've integrated two existing control frameworks, one for walking trajectories and another for kick trajectories. This allowed us to create a controller that can generate any kick motion in an arbitrary direction while also maintaining the robot stable, all while the robot is walking. With these ideas, we expect the robot to reliably and accurately walk kick. The walking engine used for this research, proposed by Seekerter and Visser, is a closed feedback loop system that uses the equations on the slides to predict the trajectories of the center of mass and use it to control the center of mass from leaving this trajectory. The estimation of the center of mass is predicted by a particle filter, and it has a torso angle controller that maintains the robot in its reference trajectory. The estimation, basically, the step planner is also optimized using Newton's method to maintain the velocity of the robot throughout the reference trajectory, and all these ideas will become relevant for the walking controller proposed in this research. So this is the dynamic kick engine framework used for this research, and it has many components such as stability controller and optimization framework to optimize the parameters in the kick trajectory. For the walking controller, we utilize the spline trajectory controller to generate kick motions that allow the robot to kick while walking. The spline trajectory generator utilizes different splines to generate kick motions. The spline used for this research can be generated and has cubic polynomials with a biopoint acting as knot for the both polynomials. The coefficients can be used to generate constraints, and the constraints of the kick trajectories are used to control the position, velocity, and acceleration of the kick. It is also used to control the height of the foot from the ground at the biopoint. The figure at the top left shows an example of a walk kick trajectory. As the robot is walking, the kick trajectory generated is constrained by the goals of the step planner. X start and X finish are two positions given by the step planner. The kick motion generated are these 2 points and then a biopoint that allows the robot to reach the point of contact with the ball to generate kick motion. So rather than allow the step planner to interpolate between XS and XF directly, the kick controller stretches out the biopoint such that it allows the robot to kick the ball and then reach the endpoint of the step planner request. So basically, the biopoint could be put in any point in 3D space, and the kick trajectory interpolates between those points, which essentially generates the kick motion. So this is the idea behind the research that enabled the robot to walk kick. Since the walking model does not make any assumptions or have a model that utilizes the feet positions, it allows us to integrate various technologies without invalidating the model of the system. So when the agent sends a request for walk kick, the motion request is received by the step planner, and the step planner chooses the next steps of the gate cycle that minimizes the amount of time to reach the reference trajectory, which is dictated by the model, which in this case is the linear inverted pendulum model. Therefore, if the agent requests a kick while the robot is walking, the step planner has to plan for the kick motion while guaranteeing a stable walk. And in order to do this, the step planner waits until the current for the kick motion, which is in the swinging phase. And when this is the case, the step planner sends a kick direction. And when the swing foot of the phase of the kick starts, the walking engine communicates with the omnidirectional kick controller to generate kick trajectory. So to test the validity of the integration of both the kick and walk controller, we designed 2 experiments that tested the reliability of the kick trajectories and the ball trajectory, while also testing the stability of the system while it generates these motions in the course of walking. The first experiment conducted was to test the performance of the kick controller while the robot walks. And in the second experiment, the stability of the robot was tested by observing the center of mass trajectory. The experiments were done in a soccer SPL field for 10 kick directions, front diagonal, back diagonal, and side for the right and left foot. By diagonal, we mean 45 degrees, but in either case, you can generate at any angle. The experiments were done with SoftBank's now V4 robot, and it was placed on the field such that the kick direction was perpendicular to the goal line. For example, for the front kick, the robot was placed facing the goal, and for the side kick, the robot was placed parallel to the goal line. For all kicks, the robot was placed by the half line. And on the other hand, the ball was placed near the kicking foot of the robot, and the robot walked roughly in place for several steps and kicked. When the robot walk kicks, the controller times the amount of time it took for the robot to generate the kick trajectory, and the ball trajectory was timed with a stopwatch. The X and Y distances of the ball trajectory was measured on the field using a laser instrument, and the measurements were taken with respect to the kick direction of the robot. This was done 30 times for each direction and for each foot for a total of 300 kicks. And it was done in various days to grab all the data on the physical robot. So this is just a demonstration. There's no audio, so there's supposed to be audio in this video, but so yeah, this is just a demonstration of various directions. It's not exhaustive, but it does show various kicks. So here's an example of different kicks. In the line. Okay. So the attempt here was for the robot to kick in all directions, just to show the ability. It was a very hard task to do, so please remind me. For the back, later frames, you'll see it better. Okay, so this is a slow motion of the robot trying to attempt a right back kick while walking. Okay, so it seems to miss, but actually didn't. But yeah, here's the right back in slow motion. And you get to see it again. So that's a right back. You see a left back. Okay. And so this is just the results of the experiments for all three. These are all the 300 kicks plotted during the course of about 3 days. And so this is a figure showing the results of all 10 directions, showing a total of 300 kicks. And each graph shows the result of 30 kicks for each direction, and it's ordered spatially. So for example, the top left graph shows the result for the left front diagonal kick. And the axis of the graph is the X and Y plane, where the y-axis of the graph is the kick direction normal. The color references the velocity of the ball, where blue is the minimum and yellow is the maximum. So in general, the results of the walk kick was very stable, regardless of the type of kick direction, with only 2 out of 300 kicks that resulted in a fall. So 1 right front kick and 1 right back kick resulted in a fall, which is less than 1%. The intended ball direction was consistent, with an average absolute bearing of less than 6 degrees, which shows that the walk is able to kick in any direction relatively accurately while the robot is walking. These figures and table show the statistics of the graph from the previous slide. The mean of the range for all kick directions is 106.2 centimeters. The mean of the bearing for all kick directions is negative 5.7 degrees. The mean ball speed is 0.52 meters per second. All back kick directions were actually the strongest of all, with an average range of 138.6 centimeters compared to an average mean of 84.6 centimeters for the rest of the kick directions. But we're less reliable with respect to kick direction, with an average bearing of 6.1 degrees compared to an average bearing of negative 5.4 degrees. We also did a correlation test using the Spearman rank correlation coefficient and found no significant results for range and bearing, but found a significant correlation between range and speed, which is as expected. The histograms of the correlation matrix were also approximately normal. The because of the walk kick variability, when the robot walked up to the ball and kicked, it was possible for the ball to take curved trajectories. And although this might have been possible, we took the measurements as if the balls traveled in a straight line. So, but overall, these statistics show that the range and speed were correlated. So at least our experiments are validated. And most of the densities for range, with the exception of left back and right back diagonal, are normally distributed. Because the experiment was done from a position where the robot had to walk up to the ball and kick, the contact with the ball was mainly inconsistent, and so most of the kick direction densities were negatively skewed. And that can be verified in the table. And the bottom density of the figure shows the density of the bearing for all kick directions that were below the alpha value in the Anderson-Darling test. Even with random ball contacts, most of the densities of range and half the density for the bearing were normally distributed. But basically, in summary, the slide just shows that the experiments are validated and the distributions show it shows what we expected. So these graphs here summarize the results of the walk kick stability analysis with the center of mass trajectories in the x and y axes are shown. Each graph shows 30 center of mass trajectories for each kick direction's x and y axis, where the average trajectory is highlighted. Every combination of the graphs describes a unique kick direction where even the kicking foot can be derived. And as can be seen in the graph, all the y-axis kick trajectory, as shown in figure C and E, moved as expected. As the robot kicks a center of mass, the center of mass shifts on the positive y-axis in figure E, such as the left side, left front diagonal, and left back diagonal, because the swinging foot leaves the center of the robot, while also showing that the center of mass stays in the center of the support polygon. When the robot kicks in the negative y-axis in figure C, such as the right side, right front diagonal, and right back diagonal, the center of mass shifts towards the negative y-axis. So when the robot kicks on the x-axis and has a constant y value, as you will see in front and back kicks, the center of mass is relatively close to 0 on the y-axis. Since all these kick trajectories can be classified with a set of mass trajectories, the combination of two center of mass trajectories can explain a unique kick direction. For instance, if the robot would execute a left front diagonal kick, we expect the center of mass to shift towards the positive x-axis, figure F, and positive y-axis, figure E. The same can be said for any kick direction, and this concept was supporting the experiments conducted. An important question that is raised is where the robot becomes unstable with all these shifts of center of mass. As can be verified in these graphs, the center of mass for the 300 kicks were bounded between negative 2.0 to 2 centimeters, in which the supporting foot trajectories in figures G and H were bounded by negative 6 to 6 centimeters, which shows that the center of mass was always in the support polygon of the robot. This verifies why the likelihood of the robot falling with wall kicking is less than 1%, and actually you can use these graphs to then create controllers that can control the trajectories of center of mass and actually generate kicks while walking. So in summary, although a variety of kick techniques have been implemented over the years, there are none that demonstrate an omnidirectional kick motion while walking. We developed a walk kick controller that enables the robot to kick in any direction while walking, and the walking controller was tested on a now V4 robot by kicking in 10 directions for each foot. We showed through experiments that a robot can walk it reliably without falling almost 100% of the time, and verified that the walk kick trajectories were consistent with an average absolute bearing of less than 6 degrees, which shows that the walk kick is able to kick the ball and walk, and the center of mass trajectories were also very stable within the bounds of the step trajectories. The step trajectories also follow the reference trajectories while executing the kick motions with a consistent average trajectory. The research conducted in this paper provided interesting results and possible research directions for the future. The momentum of the robot causes the stability of the robot to vary when it walk kicks, and analysis of this instability in relationship to the momentum of the robot needs to be considered to develop controllers that can deal with these types of forces. Currently, in order to maintain stability, the robot has to decelerate because has to leave because if the forward momentum of the robot increases, the robot may fall. Therefore, optimizing the step liner to minimize the instability while maintaining the reference trajectory will be essential. The current controller for the walk kick is open loop, allowing the robot to passively use the momentum to generate kicks while walking. But the momentum of the robot and the kick trajectory acceleration can be actively controlled to generate desired momentum, allowing a closed feedback loop system. For example, this controller will also enable passing capabilities by controlling the force of the foot when it is in contact with the ball. And lastly, testing the dynamics of the walk kick on different platforms will be important to determine the causes found in this paper and verify the system as a whole. Thank you.
Very good talk. So now we have time for a few questions. Any questions?
Thank you. Thank you very much for interesting your presentation. Open the slide with the experiment. Next, the table of experiment. Yeah, thank you. I see the front take ball speed, the lowest 0.37, and the back diagonal, the maximum speed is 0.65. Why faster back diagonal
so why
so to front?
Why is there variability, you mean, between minimum and maximum? Or
maximal, yeah.
why is there, yeah, so like for example, for the back kick, you're saying why does this maximum here exist? Or, right?
Yeah.
Right. So, yeah, so the actual densities for like speed were very variable, and that's the case because of the robot having to walk up to the ball and kick. It didn't always kick in the center of the foot, and so some balls might have been really slow and some might have been really fast. And so that definitely affected the distribution of the speed of the ball as it made contact with the ball. So that, I'm sorry, I'm not sure that explains the variability here on the different graphs.
Okay, any other questions?
Okay, so Eric asked about the backswing. So in your demonstration, the robot tend to kick very short to a kick. But in the case of humans, we usually we use backswing before the kick. So that kind of thing is, can be realized in the future direction in your last slide.
Yeah, so that's implicitly here where we talk about the actual controlling the momentum of the robot. If there's a closed feedback loop where the robot's controlling the momentum, we're actually able to generate those kind of like high level momentum, and then being able to monitor the trajectory of the center of mass to be able to do that while still maintaining the robot stable. So definitely that is a future direction that we can take.
So we have the last question. So now I have a question. You use the COM approach. So what would be the challenge if you use ZMP?
So I use the ZMP controller for like a stationary kick, but because the wall kick is already optimizing the center of mass trajectory, there is actually it's not necessary because it already has a torso angle controller. Because of that, it allowed me to generate these kicks without having to monitor the stability.
Okay, thank you very much.
Yeah.
So let's put our hands together to thank the speaker. Thank you very much. So is the second speaker here?
It follows the slide. Does it?
I didn't realize.
It just
That was
changed.
always blue.